All right, let's finish up with number 5. You're going to draw Lewis structures to represent each of the following formulas. Let's start with ammonia, NH3. Right, first we're going to represent nitrogen as having 5 valence electrons because it's in main group 5. That's how we know that. And because there are only four locations to place those electrons around that central nitrogen, that means 3 of them are going to be unpaired. 2 of them will be paired up. Well, because there are 3 unpaired valence electrons around nitrogen, that means that nitrogen can form 3 bonds. Guess what the nitrogen is going to bond to? The 3 hydrogens. So we represent the electrons electrons involved in the bond with a line, and then we just have the 2 dots to represent our lone pair of electrons. Looking at H2O, oxygen has 6 valence electrons. I can tell because it's in main group 6. And so as I fill each of those 4 available orbitals, right? Remember, there's 1 orbital coming from the S sublevel, and there's 3 orbitals coming from the P sublevel, so that's a total of 4. There are 4 sides to the letter. You can think of it that way. 2 of the orbitals will be doubly filled. 2 of the orbitals will be singly filled, which is perfect because each of these hydrogens is bringing 1 unpaired valence electron to the party, and so we will form 1 bond. Right? Each hydrogen will form a bond with the oxygen. The oxygen will form a bond with 2 hydrogens. Move on to C. We have CH4. This is methane. Now, carbon has 4 unpaired valence electrons. It's got 4 valence electrons because it's in main group 4. And so those are 4 unpaired valence electrons, meaning it can form 4 bonds. Well, we got 4 hydrogens to deal with. That makes it nice and easy. We simply form 1 bond with each hydrogen. Let's slide down to D. We have C2H2. This one is going to start getting a little bit tricky. So we have 2 carbons. Now remember, anytime carbon is present, it's going to be the central atom. But here there are 2. So we're going to start by having the 2 carbons in the middle. Okay, 2 carbons in the middle, as you can see they are here. I'm going to place the 2 hydrogens on the outside because I know that carbons are supposed to be central. That means anything else is going to be on the outside. Now, in terms of making my bonds, it's going to be, you should know that carbon is going to have 4 unpaired valence electrons. And so one of those unpaired valence electrons is going to form a bond with hydrogen. Okay, and so we can see that each carbon does have, in fact, 1 bond with each hydrogen. But after the carbon forms that 1 bond with the hydrogen, it's still got 3 unpaired valence electrons left. And so there are 2 different carbons here that each have 3 unpaired valence electrons. So each of those valence electrons is going to pair up with a valence electron from the other carbon. Since there are 3 unpaired valence electrons in each carbon, we're going to form 3 bonds. And so that's how we know that we have a carbon-to-carbon triple bond. All right, let's end up with E. It's CH2O. And so we have central carbon. Okay, central carbon. Carbon's present, so it's always central. We have to put 2 hydrogens around it. And then 1 oxygen. And no, it does not matter if you drew the oxygen over in this spot or in this spot or coming down here. What matters is the number of bonds coming out of the carbon. Its 3-dimensional orientation is not important here. What we're really caring about is that each hydrogen has a single bond to the carbon, right? So this carbon now has overall 2 bonds, right? 1 from each carbon. So that means that there are 2 unpaired valence electrons on this carbon left. Well, lucky thing, because there are 2 unpaired valence electrons coming from this oxygen, and they'll all bond up to create a carbon-oxygen double bond.